Thanks for the opportunity to present a summary of this project. It's actually an umbrella project. So there are 9 sub-projects within it. And each one of those, I could give a presentation like the one Ilbin just gave, spending 15, 20 minutes just highlighting the results and some key findings. And so there's just not time to go into a lot of detail. My goal then shifts to just ensuring that you guys know this work was done and to give you some highlights and just let you know what studies were done and highlight a few things. So this is the Fire Smart Vegetation Management Decision Support Research Project. And again, it's an umbrella project, so included a lot of people from my team, Wildfire Analytics at the U of A. And we have a bunch of research collaborators from Argentina, as well as from the Faculty of Engineering at the U of A. And the contributors from Alberta Agriculture and Forestry, it was primarily Dave Schroeder who was helping us along throughout the whole project, but there were some other folks from AAF as well, including the AWFIP crews that made contributions to some of the projects. And the funding, of course, was from the Alberta Agriculture and Forestry through the Canadian Partnership for Wildland Fire Science. So this is a 3-year project, and it's probably a great example for some of the challenges projects face in terms of timelines, when grant agreements get signed, when the money actually becomes available, and the timing of that in relation to when you can actually get a student started. We were plagued by some of those issues in terms of trying to finish this work in 3 years. But the project really kicked off in terms of access to the funding in March 2018, and then we wrapped up earlier this year at the end of March. And over that time, we involved over 18 people directly on these the various projects, and that included 11 trainees, so either students or research assistants, which NSERC likes to call HQP, those highly qualified personnel that we're training. So yeah, 9 projects so far. There's been 7 publications produced, 2 are published, 5 are currently in review with the journals. Our total expenditures were just over $350,000, and that works out to about $39,000 per project. And I wanted to get this up, right at the front because it's so important, I think, to highlight that the research money that we're getting is enabling, really interesting collaborations across disciplines. In this case, with researchers out of engineering and data science, and it can lead to some really diverse activities. And a lot of training for HQP, those trainees and students. So I'm going to list, I've listed here just the publications that have been prepared to date, and I'm going to highlight some of the results from the first 6 of those. So we did a review paper to kick things off, and then we did some rapid assessments of fuels in 2 studies, looking at both crown and ground fuels. We looked at assessing fuels with Lidar. And then we did 2 papers related to the Alberta Wildland Fuels Inventory Program, documentation of that data. So actually publishing the data set and proper documentation and for a curated portion of that data set, and then doing some analysis of that curated data set. And then there's some smaller studies that were funded in part by the project. So some fire perimeter modeling. I won't get into that. There won't be time. And there was also 2 other studies that I'm not going to talk about. One, Jeff Webber had a segment of this funding to do some work, and I believe he's going to be speaking at another time to give an update. So I'm not going to touch on his work, but it was funded under this project as one of those 9 pieces. And then also Andrew Sack is an MSc student who's been working full-time and will be coming back to finish his thesis. So I don't want to sort of steal his thunder. I won't talk about Andrew's work. But I will touch on the first 6 of those 9 projects. One of the first things we did, which I would highly recommend for a project of this scope, and I found it just invaluable, was right before the project started, we did a half-day workshop with 25 representatives from Alberta Wildfire, folks that are involved in actual fuel treatment planning and implementation, and we tried to learn their processes and understand their needs. And there's just so much. I could spend my whole 15 minutes here just talking about that workshop. It was fantastic. I wish we could make time to go back and do more of that. And I know it's a time commitment for you guys, for Alberta Wildfire. But yeah, it was invaluable. And just some of the key things that they highlighted for us was they needed science-based evidence to support the field treatment and planning and implementation process. They wanted evidence to demonstrate the change in hazard for when you're carrying out these projects. And also there were some concerns about monitoring and maintenance and long-term sort of, as these fuel treatments are being done, we need to do more to look at what's happening over time in terms of monitoring and maintenance. So the first thing we did, of course, was a review paper to just summarize the state of the science and look at the available modeling frameworks and data needs around providing some of that evidence-based insight into fuel treatment planning. And this is just a graphic from the paper, but one of the key things that we were doing here was pointing out there's some really key attributes that you need to know about fuels in order to do any kind of predictions or planning about fuel treatments. So the crown fuels, the crown fuel load and crown bulk density, the separation between the ground and the base of the crown, what we call the crown base height, and then surface fuel loadings. And you can plug these variables into existing fire behavior models, Van Wagner and Byram models, and those are the same models embedded within the FBP system. And you can look at how when you vary surface fuel consumption, how that's going to impact whether or not the fire can transition to the crowns based on critical surface fire intensity. So that's Van Wagner's model. And you can sort of see as the rate of spread increases, as conditions get more extreme, you're going to quickly exceed those thresholds and become a crown fire when you have surface fuel consumption going, from the low end up higher. So it was these kinds of graphics and assessments and examples, sort of illustrative examples that we did in the paper to try to help people understand the limitations of fuel treatments as well as the data needs for plugging into these models. Then we started addressing sort of one of the key barriers to doing these kinds of models and getting this kind of insight, and that's that you need data to plug into the models. And we know from the Alberta Fuels Inventory Program, field sampling is costly, it's time consuming, it's resource intensive. So one of the things that we really focused on with this suite of projects is, can we do things in a rapid, simpler, kind of low-cost manner in order to get these estimates that are so necessary to predicting fire behavior outcomes from fuel treatments? And there's a well-established approach to looking at rapid fuel estimation based on photos, based on visual assessments of the fuels. And we wanted to sort of extend that kind of stuff and see, well, can we develop some rapid methods, alternative methods for estimating fuel loads that would help with answering some of those needs that practitioners have. So looking at characterizing fuels both before and after treatments and over time. We wanted to do things, and this has sort of been my motto in recent years, that are simple, accessible, understandable, fast, and inexpensive. And that's the challenge whenever you're doing research. But we started with looking at field-based alternatives to characterizing fuels so that you could do it opportunistically when you have people on the ground. And so we wanted to develop protocols that were consistent or compatible with the operational situations where you might have somebody in the field on the ground. Maybe they're going out to a site to do some fuel treatments or to assess the area. And could we develop some relaxed protocols for characterizing the fuels using inexpensive equipment? And could we do that in a way where we could automate the data collection and the processing and just make it easier to characterize fuels, to measure fuels in order to inform the fuel treatment planning process? And then we also looked at emerging technology for characterizing fuels, so Lidar, satellite, and UAV imagery as part of this project. So the first thing that we did was rapid in-stand crown fuel measurement. And so this paper just came out about a month ago in Methods in Ecology and Evolution. And so this is a practical tool that we developed, and we were using smartphones, an iPhone 7, cheap, refurbished one. We bought them for about $400. And then this just fisheye lens attachment to clip onto the phone. Took in-stand upward photos using hand leveling, no tripods. And we also worked with a researcher in Argentina to overcome the barriers to doing this kind of photo acquisition when you don't have ideal conditions. So it's overcast conditions or clear conditions or partly cloudy conditions. Take the photos at any time. Can you still get useful results that would allow you to get an estimate of, in this case, I'm showing canopy fuel load estimating with just using a photograph facing upwards. And we got a really good relationship for the boreal spruce kind of fuel type. So this is a way to go into a stand, you take a picture, and you can get a rapid estimate of canopy fuel load. And that could be done before and after the fuel treatment is done, monitoring changes over time and that kind of thing. So the other thing we tried to do, well, since we're in the stand taking those upward photos, let's take some downward photos. And then we worked with some collaborators in engineering to see if we could teach a computer to classify ground fuels and the extent of ground fuels and start to characterize ground fuels. Whenever we have an opportunistic situation, we can just snap a photo, get a better feel for the kind of ground fuel conditions that we have in stands. And so initially we're just looking at just the ground cover, the proportions. And so you can see we would take a photo and then manually classify it and use those manually classified photos to teach a machine to classify it. And the machine does it really, really well. So you can get, great classification of the automated classification of the photos. Then we tried to relate it to the field measurements. And so, the machine can classify things wonderfully, but does it actually give you a picture of what field crews recorded when they were using traditional field methods to classify cover? And the relationships were actually pretty good. So this is some pretty innovative work using very advanced methods to do image segmentation in an automated way. But we think we've shown at least that there is potential to potentially capture across broad areas information about fuel, ground fuel characteristics, just simply using photographs. So the other thing that we were doing for rapid fuel characterization was to look at LiDAR. So this was Hillary Cameron's MSc thesis. And so she looked at the ground fuel, or sort of the ground measurements of crown fuels, and then related those to LiDAR metrics. And so this little graph that I'm showing here is showing her predictions of canopy bulk density using LiDAR versus the field measured canopy bulk density. So if those matched perfectly, if her prediction was perfect, it would be all along that straight line. Predictions are pretty good. And what that model allows her to do, and I'm just showing the one that she estimated for canopy bulk density, but she did it for crown fuel load and other canopy metrics as well. Basically, this is the Pelican Mountain experimental area. And you can see the whole area would be classed as the FBP system fuel type C2 boreal spruce. But you can see within that boreal spruce field type, Hillary's model using LiDAR allows her to create this continuous map showing the variation in canopy structure throughout that area in both the treated and untreated stands. So again, this is just a way to get estimates of fuel structural conditions without actually having to be on the ground and measure it. Now there's this model, and it can be estimated from LiDAR data. So another study that we did was to document the AWFIP data, the Alberta Wildland Fuels Inventory data. And this is something that we actually tried to do in an earlier project and realized that it was a lot more challenging than anyone might have imagined. And so that project was sort of rescoped. And so we tried to address it here. I had to engage some really advanced data scientists, Nathan Phelps, who came in with, he already had a master's degree. And so was quite qualified to take this on, but it was an extremely challenging part of the project to take the AWFIP data and to basically to curate it and quality check it, and then develop and do the calculations for fuel loads. And so we've done that, and we've created this database of cleaned and quality checked data from the AWFIP program. And it's been submitted as a data paper for publication. It's currently in review. It includes 476 sampling events. Each sampling event has 42 variables associated with it, and we've calculated fuel loads, including surface, understory, canopy fuels, and so forth. And so this is, I think, hopefully people recognize this will be a big step towards ensuring there's more research done with this data. So we encountered enormous challenges creating a data set that was valid for doing analysis, because this data wasn't collected for research purposes, and there was enormous issues with a program spanning 10 years, protocols changing, the way the data was recorded. There could be a lot of inconsistencies or inaccuracies that we had to hunt for and search out and clean. And Nathan Phelps did just an absolutely amazing job on this. He was the perfect person for this project. And yeah, it's unfortunate we don't have time to have him actually presenting the work, because we then used that data in a fuel classification analysis. And so that paper's also been submitted for publication. Basically what we did is we took that clean data and we asked ourselves, could we define fuel classes based on the data? So right now, everybody uses the FBP system fuel types because we have a system for predicting fire behavior based on those fuel types. So this project was all about, can we then look at the data where we have measurements of crown base height, surface fuel load, and crown bulk density, and see what fuel classes emerge from that data? And that's what we did. And so we defined 4 fuel class clusters based on the data, based on the field measurements, right? And you can see how they group out there. So red is low surface fuel load, low crown base height, low crown bulk density. Blue, low surface fuel load, high crown base height, low to moderate crown bulk density. Black, low surface fuel load, moderate crown base height, and high crown bulk density. And then green, high surface fuel load, low moderate crown bulk base height, and low crown bulk density. And so you see that if you're looking at stands structurally, they break out into their own groups based on their characteristics, right? And these fuel class clusters explained more of the stand-to-stand variability in fire behavior than the fuel types did. So I'll just show you one example. So here's the fuel class clusters on the left. You can see they form these sort of, by color, you can see they're formed together in these different groups. When you look at what those each point would have been classified in the FBP system, you can see that the FBP system fuel types are not grouping out based on fuel structure characteristics. And what that means is that our fuel class clusters aren't divided out by FBP fuel type. Within, the red grouping, you have C2 and you can have C3 and other fuel types based on their structure. So I wish I could go into more about this work. There's some this is just sort of glazing over the findings, but just to be aware of it, and I'm hoping that a lot of these studies we had planned to present if Wildland Fire Canada 2021, the conference had gone ahead, but it's not going ahead this year, so we may be able to present it next year. So just very quickly, some lessons learned, and I'm going to just give you a quick highlights of some other things we're doing. One is that the best results are achieved with, I think, with ongoing agency involvement throughout the project. And I really have to thank Dave Schroeder, who, none of this work would have been possible without his dedication to this project and his willingness to be available to work with us, to understand needs, to understand data. And he was also heavily engaged with the students and students' projects. And, that kind of commitment by the agency to have a science representative that can be available for projects, I think it's essential. Also, the other thing is that one of the things I've sought to do, and that's sort of some background to my collaboration with ILBIN, the prior presentation, is to collaborate with non-fire experts and to try to bring them in to our world and get them working on our data. So, I've worked with ILBIN trying to, get operations researchers working on our fire data, but also in this project, we were collaborating with data science experts and engineering, and there's high risks and costs to doing that. It takes a lot of time to work with people who don't have a background in fire and help them understand our problems in our data. It takes time by the agency, but also by researchers like me that are trying to create those collaborations. But in the endless conversations that I've had with some of the engineers and others that don't have a background and trying to help them understand fire, the flip side of it is I think it's high reward. And I think the more we open the doors and try to bring people in with different skill sets, that long-term there's high reward to doing that. I think there's also going to be a lot of rewards from this project that go well beyond the immediate project results and the publications. The long-term research capacity that we've helped to seed, that's going to continue to grow. And it's also created opportunities for Alberta Wildfire to benefit from subsequent work that I'm going to do that's going to build on this stuff. And the other thing is that implementation takes years, and we're just at the stage where we're publishing the papers. There's 7 of them that have been submitted. There's more to come, but it takes years to take from that publication stage and turn it into something useful that you guys can implement on the ground. And so I guess just be patient with us. And the other thing is that research scope timelines and agenda really need to be adaptable to emerging data challenges and limitations, and we have a lot of them with this project. And sort of my personal sort of request is that dealing with inflexible project start and end dates is I think in the end, it's undermining research efficiency and the quality of what you get. So if there's any potential to be flexible around those things, because we deal with a lot of constraints in terms of project startup and end. I'm doing a lot of other stuff with my team, Wildfire Analytics. Check out our website. I try to keep it up to date, but we're doing some really cool fire pathway assessment stuff with with funding from the Institute for Catastrophic Loss Reduction, AWFIP for MSc thesis, and we're getting some really neat results. So you'll see that stuff soon. I've been funded by the National Research Council to do a national hazard and exposure assessment method. I have produced an exposure map for the whole country at a 30-meter resolution, if anyone's interested in seeing that. And I'm doing some strategic evacuation planning and containment line planning work in collaboration with Amy Kim at UBC, and that's funded under the NSERC Strategic Network. And there's lots of stuff coming from that, but we want to expand that evacuation planning work and are looking for funding. We've got proposals in. We've tried to sort of stir up some interest from the agencies, but if there's interest in that topic in particular, we want to move forward with that. And I'm also, I've got some proposals in seeking funding for some community protection planning research that I'd like to move forward in the years ahead. So lots of opportunities to work with us. And I'm sorry, I think I ran long there, but thank you for listening. And if there's any questions, I can take those.